We're now going to cover the strategy pattern. In this discussion, you'll understand how the strategy pattern works in general, and you'll also learn how to recognize how the strategy pattern can be applied to encapsulate the variability of algorithm and platform behaviors via common object application programming interfaces, or APIs. The purpose of the strategy pattern is to encapsulate variability of behaviors via a common API whose implementations can be changed transparently to users of those abstractions. We'll be using strategy to decouple the interface of a behavior from its implementations. Let's start by talking about this in the context of our expression tree processing app. Certain behaviors of this program need to change in response to different user requests and runtime platforms. For example, different algorithms are needed to traverse the expression tree in different orders. In the discussion we had on Iterator, we focused primarily on pre-order traversal, but it's also important to be able to print and evaluate the tree in order, post-order, and level order. Likewise, we have different input and output mechanisms in order to be able to deal with the different runtime platforms that our expression tree processing app executes in. For example, the Android user interface environment has a different way of getting input and output than command line versions of our program will. And so we'd like to find some way of being able to abstract away from that variation in behavior. The problem here is how to avoid hard coding certain implementations of these behaviors in such a way that any changes we had to make later would require obtrusive modifications to support the alternatives. For example, we certainly don't want to have a situation where we hard code ourselves only to support pre-order iterator traversal, as we had done earlier. So we'd like to find a way of being able to add new traversal algorithms without changing anything in our code. We also want to find ways of being able to support different runtime platforms. We'd like to be able to have the code be the same and then be able to somehow parameterize certain elements of it depending on what runtime environment we happen to be using at any given point in time. So what's the solution? We'll create an abstraction for selecting one of many behaviors. Here's how we can do this. First, let's define a family of behaviors. For example, the algorithms for traversing an expression tree in various orders can be thought of as a family. They have many things in common. They just vary in terms of the order, but the idea of looking at each element one at a time in some order is similar for all the different traversal algorithms. Once we've identified the family, then we're going to encapsulate all these behaviors within a common API. In our case, we'll use the Java Iterator interface as our common API. And then we'll go ahead and make implementations of these behaviors interchangeable. We want to be able to have different traversal orders, all implementing the same Java Iterator interface. Strategy will allow us to encapsulate multiple pluggable traversal algorithms via this common interface. Next, we'll apply some creational pattern to select the desired behavior in a particular context. In our particular case, we'll apply the factory method pattern in order to decide which of the particular implementations of these different traversal strategies we want to use in a particular environment. Let's take a quick look at the strategy hierarchy overview that we're going to define here. At the root of this hierarchy will be the Java Iterator interface. And as you can see, that has methods like hasNext, next, and remove. And then underneath that will be the various implementations of this interface. These define things like pre-order iterator, level order iterator, in-order iterator, post-order iterator, and so on. And then we'll also define in the implementation of these different strategies the implementation details we need to make them do the appropriate behavior. For example, for the level order iterator, we'll use a Java queue. For the other types of iterators, we'll use a Java stack. And these will all be used to perform non-recursive tree traversals in an iterative way. From a commonality and variability point of view, the Java Iterator interface defines a common strategy API, and the implementations of this interface are the variability portion. They're able to define concrete strategies that behave in different ways, yet all conform to the common interface that was defined by the Java Iterator. Not surprisingly, this way of arranging the software corresponds nicely to one of the Gang 4 patterns, the strategy pattern. The intent of this pattern is to define a family of algorithms, encapsulate each one, and to make them interchangeable to let clients and algorithms vary independently. It's worth noting, by the way, that we use the word algorithm here rather loosely. This pattern is useful for other things besides full-blown algorithms. You can use them for little snippets of computation as well. You should consider applying this pattern when certain conditions hold. When an object should be configurable with one of potentially many algorithms, and all the algorithms can be encapsulated, and you can come up with one interface to cover all the encapsulations. We'll actually see later how you can make a few slight variations to this, but these are basically the conditions that need to apply for this pattern to be useful. Let's talk about the structure and participation. As you can see, the pattern is broken up into a couple of pieces. There's something that's called the strategy portion. That's the most interesting part. That's the part that defines the interface that does the actual behavior. In our case, we implement this using Java Iterator, which defines those operations we talked about before that involve iteration. We then have a number of concrete strategies. These include things like pre-order iterator, post-order iterator, level order iterator, and in-order iterator. And then finally, there's something else that's part of the pattern that's called the context. We don't actually use that in our particular expression tree case study, but this is useful if some strategies need to have more information that can be conveyed by the common API. We'll talk about that when we get to the implementation portion. So let's take a look and see how we might apply the strategy pattern for our Java case study. What we're going to do here is we're going to start by generalizing the makeIterator factory method in the expression tree class to return the iterator strategy that's requested by the user as a string or perhaps an enumerated type. What we do in this particular case is we modify this ever so slightly to have something called an iterator factory, which we'll talk about later when we talk about the factory method pattern. And it's got a factory method called makeIterator, and we pass it two things. We pass it the request that the user has asked us, which could be in order and pre-order and so on. And then we also pass it the object for the expression tree. That's the aggregate that will actually be traversed by whatever strategy we're going to create. This particular approach uses a factory method based on the command pattern to create the requested strategy, which is used as an iterator to access each node in the composite expression tree. That's a bit of a mouthful, but it illustrates what's known as high pattern density. This particular piece of code has 4 or 5 patterns all coming together to help justify and document how it's designed, and more importantly, why it's designed in this particular way. What we're going to do now is we're going to take a look at some of the different uses of the strategy pattern in our expression tree processing app code, and you'll see that it's used for more than just iterators. We also use it for other parts of the application as well. So we'll talk about this here and give you a chance to see how the code actually works. There's a number of implementations of the strategy pattern in our expression tree processing app. First, just take a quick look at another example of iterator, which has been strategized as we've discussed here. Let's take a look first at level order iterator. This is a strategy that we use to traverse an expression tree in so-called level order. It's actually almost identical to the pre-order iterator implementation we looked at when we talked about the iterator implementation. The only real difference here is instead of having a stack, we have a queue, and we implement our queue using a linked list. And we're going to go ahead and just show quickly the implementation of this. Most of it's almost identical. In fact, the ironic part is that the difference between a pre-order traversal and a level order traversal is really pretty much restricted to the use of a stack versus a queue. As you can see here, the algorithm is essentially the same as for the pre-order traversal. It just goes through the queue and removes the elements and then adds them back into the queue to advance the iterator. So that one's not really that much more interesting than what we saw before. More interesting examples appear in the context of post-order iterator and in-order iterator. I'm not going to walk the details in great depth at this point. You're welcome to look at the code, but one of the things you'll notice when you take a look at the implementations of this code is we have a lot more work to do inside the post-order and in-order constructors to deal with the trees that are going to be traversed in this particular order. And the next methods are also substantially more complicated. So here's an example of the next method for post-order traversal. You can see it has a lot more work to do. If you pop over to the in-order traversal implementation, you'll see once again it uses a stack just like post-order does. Its constructor has a bit more work to do. Its next operation has a bit more work to do, and so on. The key point of all this, of course, is that using the strategy pattern in this particular case allowed us to completely abstract away from a user perspective these different traversal strategies. The actual use of these is very simple. They all look exactly the same from a usability point of view. I'll just give you a quick snippet that illustrates the use case here. We'll come back and talk about this later when we talk about the visitor pattern and the state pattern. Here's just a quick example of how we end up using the strategy pattern and the iterator pattern together in order to iterate through an expression tree and print all of its elements. As you can see here, we make an iterator using the appropriate requested strategy, and that comes back as an iterator that we can then walk through one element at a time. And you can see from this particular implementation that I'm showing here, it doesn't matter whether we're traversing the tree in pre-order, post-order, in-order, level order, or any other order. Those implementation details are hidden behind the use of the iterator abstraction in conjunction with strategy to provide different implementations of the way in which we traverse through the tree. As I mentioned before, we'll come back and talk more about this later. I want to show another interesting example of the use of strategy pattern 2 that's different from the use of iterators. And this particular example deals with trying to abstract away from the underlying platform that we are using at runtime to execute our code. As we've talked about in Lesson 2, our expression tree processing app can run really without change in both an Android GUI environment as well as a command line environment. And strategy figures prominently in that context as well. Let's just take a quick look to see how this works. Here is the main program for the command line version. And as you'll see, that this basically reuses the bulk of the expression tree processing app, just provides a little wrapper so it can run in a command line environment. We'll talk about some of these other things later when we get to other implementation discussions. But I just wanted to focus on one thing right here at the moment. If you take a look here, there's something called a platform factory. And when we go into the main part of the application, we're going to make a new platform factory instance, passing in the system in and system out input and output streams. This platform factory is used to stash that information away, and what we call the make platform method on the platform factory, it returns the appropriate platform strategy. And then we use this platform strategy for all kinds of things. Whenever we want to be able to do input and output, for example, we simply say platform.instance, which gets us the platform strategy, and then we do an operation that corresponds to whatever it is we want to do with input or output in a platform runtime independent way. Here's a simple example where we print an output string. In this case, we're using the command line platform implementation. If we were in Android, we would have a different implementation. Just for kicks, let's take a quick look at the platform factory and its main subclasses, because this also illustrates the use of the strategy pattern. Here's platform factory. Platform factory is a class that has a bunch of different things in it. You can take a look at this. I'm not going to talk about the implementation details in great length. I just want to show a few things. Here is the constructor for platform factory that takes the input and output mechanisms as objects, so they can be the root of various types of concrete classes in Java. We create a map that maps the different strings for the different platforms. The Android project is one string. Sun Microsystems is another. Oracle Corporation is yet another. And when the make platform method is called down here, we go ahead and get the name of the Java vendor. We use that name to then look up the corresponding command object in this map, and that will end up then pulling out the appropriate command object, which we then go ahead and execute in order to create the appropriate type of platform strategy. So here's one example. We have a command line platform strategy where we pass the input and output objects to that. If we were running on Android, we would create the Android platform strategy, passing the input and output objects to that. And if we take a look over here at something like command line platform, this is a concrete strategy in the context of the strategy pattern. The command line platform extends platform, and it keeps track of input and output streams, which are then passed in from its constructor. And then anything we need to do here that involves input and output uses those corresponding input and output streams that relate to writing things to a command line interface. In contrast, if we go over here to the Android platform, this is a different strategy. This knows how to deal with input and output on the Android platform. It extends the platform subclass, and it provides different ways of being able to input and output data using edit text and text view variables. And if you were to take a look down here, you can see that we pass the input and output objects into the Android platform constructor, and then we cast those appropriately to correspond to edit text input and text view output. So this is a nice example of how we can strategize how input and output are done for the different platforms in which we run using the strategy pattern. Not surprisingly, the implementation for Android is much more complicated than doing things for command line, but here's an example of how we do output in the Android strategy example. We end up doing some extra work and put things out to a text view output. And let's just compare and contrast that to the same method that we would have here in our command line strategy. So here's output line for command line. Here's output line for our Android platform. We have the same interface. The same interface is used in both platforms, but the implementations of these strategies are quite different. So by using this particular technique, by using the strategy pattern, it makes it a lot easier to write code that is essentially the same for 98% of the software, and only in a few select places, which deal with the actual user interface environment and runtime platform, do we end up having a variation and some diversity. Now that we're done looking at the way we've used strategy in our case study, let's talk about the consequences of applying this pattern in general. There's a number of positive benefits that come from using this pattern. Greater flexibility and reuse are one of the most important. For example, by strategizing runtime platform input and output mechanisms, as we showed in our code walkthrough, the bulk of the expression tree processing application code can actually be reused without change across the Android variant as well as the command line variant of the application. And that's very powerful because it means that we're able to kind of pull out the behavior of the app and its data structures and its behavior and make that parameterizable for the context in which it runs, which is a good example of systematic reuse and platform independence. You can also change the behaviors of the pattern dynamically. We don't really show this in a major way here. We don't change things as they're running per se, but every time someone comes along and makes a new iterator, we're able to dynamically create the appropriate strategy at runtime without breaking any client code. So the code here illustrates how you can have the make iterator interface, and then irrespective of what you pass into it, as long as it's something that is recognized by the factory method called make iterator, we can then write some code as a client code that will iterate through the tree in a particular way, doing something on each node in turn without having to make any changes to the client code. So it's very powerful. There are, however, some downsides of using this pattern. There's, of course, the overhead of creating strategies and communicating amongst them. So you may end up with lots of strategies. If they have to interact with each other, that can become overhead, at least in terms of the amount of classes to keep track of. You also may have a situation where having to provide a uniform interface for strategies becomes too inflexible. In the case of something simple, like what we're dealing with here, where we've got traversal orders of an expression tree, one-size-fits-all interfaces work fairly well. If you start getting into more complex environments where we're trying to do very sophisticated platform independence, it may be difficult to come up with a one-size-fits-all solution. That, to some extent, motivates the need for the context portion of the pattern, because we can use that context to store certain information, certain state, certain other options, and so on, that might not fit into the Procrustean bed of a one-size-fits-all interface, while still allowing the strategy portion to remain the same. There are some potential downsides to using this pattern, however. One of the things you have to be very careful of in heavily strategized designs is what happens if you end up with multiple strategies that can't be used together in a way that is semantically compatible. For example, if you're building some piece of middleware, you might have strategies for things like the concurrency model, the synchronization model, the event demultiplexing model, and so on. And there may be multiple implementations of each of those strategies that in isolation make sense, but when combined together cause erroneous or inefficient behavior. For example, if you chose to use a thread pool concurrency strategy, but then you turned off all the locking in the system, you'd end up with race conditions and other problems of scheduling because you mixed strategies in ways that are not semantically compatible. So you have to be very careful with that. It turns out in practice that you can often solve this issue by applying other patterns, things like abstract factory that we'll talk about later. So let's talk a bit about the implementation issues. So one implementation issue is to determine whether or not there's a need for, and if there is a need for, how to exchange information between a strategy implementation and its context. Now, if you play your cards right and all the stars align, you may be able to get by without requiring a context at all, if everything fits nicely into the strategy interfaces in a common way with common parameters. If that doesn't work, however, you'll end up having to store some of the information in the context. And you can put them up there perhaps in a hash map or something else that can be looked up as sort of a name-value type of binding, various kinds of keys and values and so on. And these are ways in which the strategy implementations can reach back up into the context to get access to other information they need to do their job without totally breaking a common interface. But it's clearly a bit of a kludge to push things into the context because it makes coupling and binding all that more obtrusive. Another consideration is whether or not to do all the selection of strategies in a dynamic way using inheritance and virtual functions or virtual methods versus more static binding using Java generics or C++ parameterized types. And there are obviously pros and cons of each way. If you read the Gang of Four book, you see they talk about some examples of using C++ parameterized types as an early binding or static binding variant of the strategy pattern. If you're a heavy user of generic programming in either Java or C++, this is actually probably a very common style. If you're a C++ standard template library programmer, you undoubtedly understand the concept of a functor, which is essentially a strategy that's bound at compile and link time to parameterize the behavior of an algorithm. So this is also another implementation consideration, and you're typically trading off dynamism for performance. Strategy with inheritance and virtual methods is more dynamic. Strategy implemented with generics or parameterized types is less flexible, less dynamic, but more efficient. Another thing that's worth noting here is that you can implement strategies in Java using interfaces and factories. Very, very common technique. We used it when we implemented our expression tree traversal orders for the iterators. We have the Java iterator interface, and then we implement that to have different various ways of providing the strategies for traversal. And we'll, of course, create those things using factories in the factory method pattern that we'll talk about here shortly. It turns out, if you start doing these kinds of things, that you find a tremendous relationship between the bridge pattern, which is an object structural pattern, and the strategy pattern, which is an object behavioral pattern. They're actually very, very similar. Bridge strategy is a not uncommon pattern compound. It turns out that oftentimes, especially in Java, people tend to gravitate more towards strategy as opposed to using bridge. So it takes a little bit of careful reading of the Gang of Four book and thinking deeply about what these patterns are doing to even see why they're not the same abstraction. But there are some differences that are worth understanding. In terms of known uses, strategy is very, very widely used. We use it a lot in the middleware that we've developed over the years because it makes it easy to develop software that has a common structure and common interfaces to vary behaviors, thereby making it possible to reuse the middleware in a much broader range of domains and use cases because you can customize and tailor the implementation details for the needs of particular styles of use. So you might want to take a look at some of the papers we published over the years that talk about how you can implement strategy in the context of reusable middleware. So to summarize the strategy pattern, strategy encapsulates the variability of behavior via a common API whose implementations can be changed transparently. And it decouples the interface of a behavior from its implementations, so it's easier to make the changes to customize your solution to meet your needs without requiring drastic surgery on the way in which the software is actually developed.